Hi, my name is Chase, and today we're going to be doing some simple kinematics problems. Number 1. An airplane accelerates down a runway at 3.2 meters per second squared for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. So we know that the plane accelerates from rest, so our V initial is going to equal 0, and it accelerates with an acceleration equal to 3.2 meters per second squared. And the time, we know, is 32.8 seconds. So now we need to consult our kinematics problems. And we need to see which one has V initial, which one has A, acceleration, which one has T, and which one also has change in X, as this is what we are solving for. And if you notice, this bottom left equation here has change in X, velocity initial, time, acceleration, and time again. So this is the equation we're going to use, and that is delta X is equal to V initial times time plus 1/2 acceleration times time squared. Now, we don't have to shift the equation around because we already have it equal to delta X. So now we can plug in our numbers. We can plug in delta X equals, that is 0 times 32.8 plus 1/2 our acceleration, which is 3.2, times our time, which is 32.8 squared. Now, the initial is 0, so that cancels. So now we have that our delta X is equal to 1/2 times 3.2 times 32.8 squared. 32.8 squared. So now, if we get out our calculator and we plug in those numbers, so we have 1/2 times 3.2 times 32.8 squared. This gives us our answer of 1,721.3. So we can put a little equals there. 1,721.3. So then our final answer would be the change in X equals 1,721.3 meters. Okay, that's question number 1. Number 2. A car starts from rest and accelerates uniformly over a time of 5.21 seconds for a distance of 110 meters. Determine the acceleration of a car. So first, we are solving for acceleration, and we have a car that starts at rest. So again, V initial equals 0, and it accelerates for a time of 5.21 seconds, and our delta X, as we know, is going to be 110 meters. So we have all this information. Now we can reconsult our 4 kinematics equations, and we see that yet again we are using this delta X equation. So let's write that down again. That is delta X equals V initial times time equals plus 1/2 acceleration times time squared. Now this time we are solving for our acceleration, which means that our acceleration needs to be the one over here, or alone. So let's do that. So we have our delta X equals V initial times time plus 1/2 acceleration times time squared. First of all, we're going to subtract V initial times time, and that will give us delta X minus V initial times time is going to equal 1/2 acceleration times time squared. Now we can divide by both 1/2, which is the same thing as multiplying by 2, or as well at the same time we can divide by time squared. So then we're going to be left with 2 delta x minus 2 v initial velocity times time over t squared is equal to acceleration. And now we know that velocity initial is 0. And since it's 0 here, it's also 0 here. So we can cross that out. So our final equation for acceleration is equal to 2 times change in x over time squared. Now that we have this final equation, we can plug in our final values. We get acceleration is equal to, it's at 2 times 110 over 5.21 squared. And if we plug that right back into our calculator, where we were before, we get a fraction. We go 110 over 5.21 squared, and that will give us 8.104. So our acceleration is equal to 8.104 meters per second squared. That's question number 2. Number 3. Upton Chuck is riding the giant drop at Great America. If Upton free falls for 2.6 seconds, what will be his final velocity and how far will he fall? So the two things we need to solve for are velocity final, which we don't know, and delta x, which we don't know. The values we do have are acceleration. If we know that he's in a free fall, we know that he is starting from rest and he is falling down with an acceleration of 9.8 meters per second squared, as that's a gravitational constant. So we plug in our 9.8 meters per second squared for acceleration. We also know the time, which is going to be equal to 2.6 seconds. Another value that we know is if he's free falling, he is starting from rest. So V initial is going to equal 0. Now, if we consult our kinematics equations, we need to find first an equation that does not have delta x, but does have final velocity as well as these other values over here. So let's consult. In the first equation, we have velocity final, which is what we're solving for, but we also have these 3 other values that we also have. We have v initial, we have acceleration, and we have time. So we can solve for the final velocity. And that is velocity final equals velocity initial plus acceleration times time. So let's solve. Velocity final equals 0 plus acceleration, which is 9.8, and times time squared, 2.6 seconds. So now if we multiply 9.8 times 2.6, we get 25.48, or 25.5. So our final velocity is 25.5 meters per second. That's one of our answers. Now we need the second answer, which is that delta x over here. So let's reconsult our kinematics equations, and let's figure out which one we should use next. Now, we could use a multitude in this situation because this is delta x, and it has all these values that we know. We have a delta x here, and we know all these values, and we have a delta x here, which delta x is just final displacement minus initial displacement. But I think for the sake of the problem, we are going to do the one without final velocity in it, just because I think that's what the problem wants us to do. So we're going to use this delta x equals velocity, no, we already used that one, so we're going to use a different one. We're going to go delta x equals 1/2 velocity initial plus velocity final times t. So we have delta x equals 1/2 velocity initial plus velocity final times time. So let's plug in. We know that we are solving for delta x, so there's nothing to be plugged in there. We have our 1/2, which is, and then v final, which is, or v initial, which is 0, plus 25.5 times time, which is 2.6. So now that, because we can cancel the 0, it simplifies to 1/2 times 25.5. So let's do that on our calculator. We have 1/2